let's say you have F1 is equal to x times L minus x, and F2 is x squared times L minus x. Let's do this for a particle in a box. What did we say the exact wave functions are for the particle in a box? Square root of 2 over L sine n pi x over L, right? Where n is 1, 2, 3, and so on. But let's pretend we don't know that. Okay, so let's try to approximate it using these two functions right here. A linear combination of F1 and F2. So what would be the best values to use for C1 and C2 so that you can get as close as possible to the correct ground state energy? What was the ground state energy, remember? It's just n squared. N is 1, right? For the ground state. So it's n squared h squared over 8m L squared. So let's pretend we didn't know this exact solution. Let's just pretend we're guessing what the function is. We're going to say, wait, our estimate for psi is phi, right? So we're going to say phi is approximately what our psi is, okay? And our phi is C1 F1 plus C2 F2. All right, so let's set up the secular determinant. What would you need to calculate? H11 would be what? Integral of F1 star h hat. What is h hat for a particle in a box? Negative h bar squared over 2m second derivative with respect to x. So that's your h hat, right? And our F2 would be, that would apply on F2 dx. So what you need to do is you apply your F2, you substitute your F2 here, which is going to be x squared times L minus x. And I'm sorry, that's F1. Okay, that should be F1. Thank you. So that should be F1. So F1 star h hat F1. So this is your F1. So what's F1? It's x times L minus x. So you substitute it there, and you substitute x times L minus x there. Okay? And you do likewise for H12, H22, H21, and then you do it for S11, S12, S22, and S21. Okay? And I'm going to go through that with you in just a little while. Let me just show you where these H11s and S11s come from first, okay? So let's do this. Remember, how did we say W? What would they say W? What did we say W was? It's going to be phi star h hat phi d tau, right? That's the integral over integral of phi star phi d tau, correct? And what's that numerator? That's just going to be C1 F1 plus C2 F2 complex conjugate times h hat applied on C1 F1 plus C2 F2, okay, divided by, you have C1 F1 plus C2 F2, and then C1 F1 plus C2 F2 down here, right? So that's your W. What do you notice there? We've seen this lots of times before. Okay, expand that. What do you get? One of the terms you would get would be what? Something like C1 star C1 F1 h hat F1, correct? And then you get a C1 star C2, and then you have an F1 h hat F2, and so on and so forth. How many terms are you going to get for your numerator? You're going to get 4 terms, right? And your denominator, you're going to also get 4 terms. You're going to have C1 star C1 F1 F1, right? Plus C1 star C2 F1 F2 plus 2 more terms, right? So this is just C1 star C1 H11 plus C1 star C2 H12. Okay? And then you're going to have a C2 star C1 H21 plus C2 star C2 H22. And then you get those four terms in your denominator. You're going to have C1 star C1, and this thing right here is just S11. Right? So times S11 plus C1 star C2 S12 plus C2 star C2 C1 H21 S21 plus, let me clean that up. You'll have plus C2 star C1 S21 plus C2 star C2 S22. Now, all of these H11s, H12, H21, H22, S22, S21, S12, S11, those are just integrals. So those are just numbers, right? So what you have here is your W depends on C1 and C2. Okay? So anyway, what happens is if you take the partial derivative of W with respect to C2, set it equal to 0. Do the same thing for partial derivative of W with respect to C1, set it to 0. Okay? You would end up with two equations and two unknowns. All right? So you would end up with H11 minus WS11 times C1 plus H12. Now, the derivation for this is kind of lengthy, but this is what you end up with. H12 minus WS12 times C2 is equal to 0. So that's your equation 1. Okay? And the second equation you get would be H21 minus WS21 times C1 plus H22 minus WS22 times C2 is equal to 0. Okay? So remember we said the H's and the S's are just integrals. Those are just numbers. Okay? And the W here is unknown. Okay? You're looking for those W's. Right? And then C1 and C2s are also unknowns. So you can express this thing in matrix form. You can say that's going to be, I'm gonna put the coefficients in one matrix, and then I'll have another matrix here. I can have H11 minus WS11 times C1. So this times C1 plus H12 minus WS12 times C2. So this term right here times this term, okay, would be equal to 0. Okay, and then you can write H12 minus WS12 times C1 plus H22 minus WS22 times C2 is also equal to 0. So this is your the matrix form of your two simultaneous equations. Okay, remember how to set things up in a matrix form? Simultaneous equations. Let me give you a simple example. Let's say you have X, let's just pretend you have, let's say, C1 plus C2C1 plus 3C2 equal to 0, and then you have 4C1 plus 5C2 is equal to 0. How would you write this in matrix form? You would say 2 times C1 plus 3 times C2 is equal to 0. Okay, and then you say 4 times C1 plus 5 times C2 is equal to 0. That's your matrix form of your equation. Okay, so this is your unknown coefficients. Okay, and this is these are actually the unknowns, and these are the coefficients of the unknowns right here. 2, 3, 4, and 5. Okay, this is where we derive the secular determinant. What we're saying is, for there to be a what's called a non-trivial solution to this, the determinant of, in this case, 2, 3, 4, 5, what's that determinant equal to? 2 times 5 minus 4 times 3. That's equal to negative 2. So 10 minus 12 is negative 2. Okay. Now, when that determinant is not equal to 0, okay, then you say the only solution to this problem is all the unknowns are 0. This is what is called a linear, simultaneous linear equations, homogeneous linear equations. All these terms are 0 right here. Your coefficients, if this determinant right here happens to be non-zero, then the only solution to this problem is for the unknowns to be 0. The only way you can satisfy these two equations right here, look at this one. What's the only way you can satisfy those two equations? If both C1 and C2 are 0. Okay? Now, if you have, if the determinant, however, happens to be 0, then you can have what are known as non-trivial solutions. So if all the coefficients are 0, that's called a trivial solution. Okay? You can have a non-trivial solution if the determinant happens to be 0. And that's why we said earlier in our, when we did this thing earlier for the linear variational method, that secular determinant must be equal to 0 in order for you to get non-trivial solutions. That means a solution where all the C's are not 0. Because if all the C's are 0, then your wave function is just 0. So it's useless. Okay? So this will give you n equations in n unknowns, and so that would allow you to solve for n possible values of W. When let's do that on MathCAD. Okay, so let's define our terms to make our constants first. To make things simple, let's just define h bar to be 1. Okay, we're going to use what are known as atomic units. Let's pretend our particle is an electron. We're define its mass to be 1. Okay, 1 atomic unit. And so what is h if we know h bar? It's 2 times pi, right, times h bar. Right? So what else do we need to know? Let's define our length to be 1 atomic unit. So let's just imagine we have a particle confined to a box of length of 52.9 picometer, 1 Bohr radius. Okay, let's make things simple. Let's just set everything to 1, most of it to 1 anyway. All right, so what do we expect the ground state to be for this particle in a box? What was the formula for particle in a box? N squared h squared over 8 times mass times L squared, right? So N is 1, so h squared over 8 times mass times L squared. So our energy in this reduced set of units would be 4.935, okay? Let's look at our functions. F1 we said was what? X times L minus X, okay? So if we were to take the derivative of x times L minus X, if I were to take the derivative of that, what do I get? I want the second derivative. So x times L minus X, take the derivative with respect to X, second derivative. That's just going to be negative 2. Okay? So that's your df1. This is second derivative of f1, right? And if I wanted f2 to be x squared times L minus x, what's my second derivative of that going to be? X squared times L minus x. Second derivative. It's just 2 minus 6x. Okay? It's assuming L is 1 here. Let's move this down here. Okay. Let me define L later. So let's make that more generic. So those are your expressions for your functions. Okay. So I'm going to define f1 of x for calculation purposes. So I'm use the assignment operator is equal to x times L minus x. Let me put that down here. What is hf1? Hamiltonian operating on function f1 is going to be equal to negative h bar squared over 2 times the mass times the second derivative, which is negative 2, right? There. Okay, let's define f2 of x. That's x squared times L minus x. What's the Hamiltonian applied on that one? hf2 of x equals negative h bar squared divided by 2 times the mass times the second derivative of f2 is 2L minus 6x. Let me copy that. There. All right, so now that I have that, can I calculate my integrals? What's my first integral? h11 equals integral from 0 to L dx. I'm going to call this L. Okay, what goes in my integrand here? f1 of x, right? Times hf1 of x. We're just assuming everything's real, so we're not even gonna bother with complex conjugate, okay? Since L is real, x is real, and then h12 is what? Integral of what? What did I put here? f1 of x, hf2 of x dx from 0 to L. Let's see what these numbers are. What is h11? h11 equals 0.167. What is h12? h12 equals 0.083. So you can see these are all of these integrals. These are just numbers. Okay. What about h21? Integral. What do I type in here for the integrand? f2 of x times h f2 of x dx integrated from 0, x equals 0 to x equals L. And let's verify what h21 is. h21 equals 0.067. Okay. I'm sorry. H21, so that's HF2. F1, HF1, right? So 0.083, okay? So this is 2, 1, so this is F2 and this is HF1. Okay. And then H22 equals integral of F2 of x times HF2 of x dx from x equals 0 to x equals L. So H22 equals 0.067. Okay, let me just make sure this multiplication sign here seems to be not clear. So times HF2 of x. So those are your H's. What about your S's? S11 equals integral of F1 of x times F1 of x dx from x equals 0, x equals L. So you have S11 equals 0.033. Okay, you might be asking, why isn't that equal to 1? We didn't, it doesn't have to be. We did not define these to be normalized wave functions. Okay, so apparently these functions are not normalized. So what? So you don't necessarily, if you see this integral right here, okay, F1 of x times F1 of x dx from x equals 0 to L, that's not necessarily going to be equal to 1 if your the functions that you're using are not normalized. Okay, so obviously here it's not normalized. What about S12? Integral from 0 to L of F1 of x times F2 of x dx. And S12 equals, oops, I need to define it after. S12 equals 0.017. And you do the same thing for S21 equals integral, this time F2 of x times F1 of x dx from x equals 0 to x equals L. And what do you think this is going to be? S21 is equal to, should be the same as S12. Okay. Then let's do S22, which would be the integral from 0 to L of F2 of x times F2 of x dx. Something doesn't like something. 0 to L. I'm going to call this S22. Okay, and S22 is equal to 9.524 times 10 to the 9th. So you have all of those. Okay? So what do we do next? We set up a secular determinant. And so what we do in MathCAD is right here under the matrix menu. This thing right here allows you to set up a determinant. And what you put inside your determinant is a matrix. So with that placeholder selected there, you insert a matrix. What kind of matrix do we need? A 2 by 2 matrix. 2 rows, 2 columns. So what are, oops, what happened? What are the elements of our matrix? It's going to be H11 minus W times S11. That's our first element. second element is H12 minus W times S12. This one is going to be what? This is row 2, column 1. H21 minus W times S21. And this one's going to be H22 minus W times S22. And this whole determinant is going to be equal to 0. For non-trivial solutions to exist, this determinant must be equal to 0. Okay? And so all we have to do now is solve for W. So go to symbolics, variable. Actually, let's expand this. Oh, I don't know if this will expand, but let's see. Evaluate this. Yeah, right there. So this determinant right here, you can see, is a quadratic. Okay? Second order with respect to W. Okay, it's a quadratic in terms of W. But we said that this entire right-hand side, this determinant, is going to be equal to 0, right? So what I'm going to say then is this determinant. Oops, sorry. Pick that up again. Copy that determinant. This is the value of the determinant is 1 over 240 minus 13 over 12,600 times W plus 1 over 25,200 times W squared. This determinant is equal to 0. So you can see there's two possible values of W's that will make this determinant, this secular determinant, equal to 0. So I just go solve for the W. W is equal, so symbolic, variable, solve. Okay, I'm solving for W. And those are the two allowed values of W. So copy that. I'm just going to say W equals that. So it's either 5 or 21. Or you can say W equals, in terms of H squared over 8 times mass times L squared. Our estimates for the two lowest energies using these two functions would be 1.013 H squared over 8 mL squared and 4.255 times H squared over 8 mL squared. And you can see your lowest possible energy is, okay, what's the true ground state energy for particle in a box? It's just H squared over 8 mL squared, right? This is about 1.3% higher. We did not get the exact energy, but we were close, okay? Now, if you add more terms to your for your expression for phi, you want C1F1 plus C2F3 plus C2F2 plus C3F3 plus C4F4. If you add a lot of terms, then you can get closer and closer to, basically, by putting more parameters in, you're able to tweak those parameters so it would more or less look like the correct wave function, and will give you a good value for your ground state energy. And what's your estimate for the first excited state? What's the first excited state for a particle in a box? It's 2 squared H squared over 8 mL squared, right? So it's going to be 4 units, and our estimate is 4.255. So that's how you would use the linear variational method to estimate the energies. Now, if you use each one of these each of these W's that would make your secular determinant equal to 0, you go back and plug this into your simultaneous equation. For each W, you can solve for C1 and C2. And then you take this other W here, 4.255, you plug it back in, you solve for C1 and C2. You want to know what the functions are. But generally, when we're doing variational calculations, we're more interested in just the energies. Okay?